So far we have looked at the compiler front end, the lexer, the parser, and the semantic analysis phase. If we look at the compiler pipeline, again, we have a lexer, we have a parser, we have semantic analysis. And these basically form, these three steps can be kind of thought of as the front end of the compiler. And the back end of the compiler is optimization and code generation. So for the rest of the course, we'll be talking mostly about the back end of the compiler. And before we can talk about these things, we will need to know what is the runtime organization. So far we have been talking about the language syntax, the language semantics, the language type system. But now we are interested in figuring out how to translate or implement this language on the existing computing substrate. And to be able to understand how to do this, we need to first understand what is the substrate available, and that's exactly what we mean by runtime organization. So what does runtime organization contain? Well, it contains a lot of things, but some of the things that it represents is what lives where. All right, so it's basically also called, and also can be also thought of as how is the storage organized. So when we say what, we are interested in figuring out where does code stay, where do variables live. For example, the programming language may support local and global variables. So where should be the space for those variables be allocated, and where should other type of memory allocation be performed from? And for example, a language like C has the notion of malloc. So where is this memory coming from? Where should it be maintained? A language like C++ has the idea of new operator, right? So once again, it's similar to malloc. A language like Java also has new operator, but there are some other languages like, for example, Python or Perl or OCaml. And these languages don't really have explicit operators, but they have implicit memory allocation. So you can, implicitly copy a list into something else, or you can start growing a list just by calling some operators on the list. And internally, there's some memory that's being allocated to be able to represent the information that you're trying to represent. So question is, where is this memory going to be allocated from? And all this basically comes under the purview of storage organization, right? And then the question is where. So one thing is what, and the other thing is where. I guess what are the options for where? And so one of the options is to store this to store these constructs, for example, code, variables, malloc memory in the memory address space. So a computer is typically made up of a memory, and there's a CPU, and recall that the CPU is basically just a loop that's going to just execute one instruction after the other. And so it can make references into the memory. And so this memory is basically can be abstracted as an address space. And so basically we were going to store much of this information actually in the address space, and that's no surprise. But then the question is how to manage or how to lay out this address space. Where should we put what, so that they can live, all these different things can live peacefully and coexist with each other. For example, variables should coexist with malloc memory and should coexist with code. Now some things can be even maintained in registers. And this actually happens a lot. Some variables will not be allocated in memory, but will be allocated in registers. And typically such decisions are made by the compiler. So what do I mean by registers? These are on-chip registers of the CPU, which are much faster than memory, and they are not represented as an address space, but there's only a small number of registers that you can access. And I guess we have already discussed such an organization of a computer. And there's a third option, and you may want to actually store some of this stuff on the disk, not necessarily in the memory address space, but maybe on the disk. And once again, for some languages, the compiler is completely not involved with managing the disk. For some other languages, the compiler may be involved in managing the contents of the disk. Typically, the disk management is done by the operating system. All right. So that's another part of runtime organization, which is who manages what. So by who, I mean, obviously it's not a person, but it is some code, right? And so which code manages what and who has written that code? And that's what we mean by who. So for example, and when I say manages what, so by what I mean who manages code, who manages the placement of variables, who manages the placement of malloc memory, and so on, right? So by who? So one of the actors, the who actors, is the code generated by the compiler. So it's not the compiler that's going to manage these things. These things are supposed to be managed at runtime, and unless we are talking about just-in-time compilation or something like that, for ahead-of-time compilers, the compiler is nowhere in the picture during runtime, and so this type of things can only be managed by the code that has been generated by the compiler and not the compiler itself. And so, some of these things will be managed by the code generated by the compiler. For example, what to put in registers and what not to put in registers is something that the code generated by the compilers is managing, right? And what is living in which register and so on. Of course, if something has to be managed by the code generated by the compiler, then the compiler also needs to manage how to lay out, how to generate that code and things like that. So ultimately it is the decision of the compiler, and in turn it's the decision of the compiler developer. But at runtime, really what is actually making the decision is the code generated by the compiler. Then the other thing is the operating system. So operating system is making decisions. For example, the operating system may be using paging or some kind of virtual memory to decide what lives where. And so this responsibility of what lives where is being sort of shared between the compiler and the operating system. For example, typically there will be the notion of a virtual memory and there will be a notion of a physical memory. I'm not going to go into these concepts because they are kind of outside the scope of this course, but if you recognize these concepts, that's great, because then you'll be able to follow this discussion. So the mapping from virtual memory to physical memory is typically maintained and managed by the operating system, but the organization of this data or stuff inside the virtual memory is typically managed by the compiler, and even there some of it is managed by the operating system and some of it is managed by the compiler. Then the other thing is, some of it could be managed by runtime libraries. That by runtime libraries, it's not necessarily part of the operating system, but just some libraries that were linked with your program. For example, malloc and free are not really part of the operating system. They're just user level libraries that can be linked against, and then that can kind of manage what gets put where. And then finally, the hardware gets to manage some of what lives where as well. For example, inside a computer, memory, although we think of memory as a single address space, typical modern computer doesn't have a single memory, right? So it actually has multiple banks of memory, and depending on what you place where, it increases the bandwidth, available bandwidth to access memory. And so some of these optimizations can be done by the operating system, some of them are done at the hardware level. For example, things like prefetching, caching, and so on. All right, so with that background, let's understand how does a program actually start, and what does the runtime look like when the program is just about to start. So initially the operating system is in control and it loads the program's code into the address space of the program. Now when I say address space, it could be virtual memory or physical memory. I really don't care when I'm looking at it from a compiler's perspective. Typically it is virtual memory because we are talking about programs that are compiled for modern for multiple user operating systems like maybe Linux or Windows, whatever. But then there are also programs that run on really small devices where there is no concept of virtual memory, and even their compilers are useful. Right? So in any case, I'm not going to worry about whether it's virtual memory or physical memory. I'm just going to call it a memory address space. And initially the OS is in control. The OS allocates memory and exports it as an address space. So we just discussed this. And so this is what, if I was to draw the address space as a rectangle, then this is the rectangle, and the meaning of this drawing is the following, that the addresses are, so each kind of horizontal row in this figure represents an address, and let's say the addresses are increasing from bottom to top. Okay, and this address space, although I have represented it as a contiguous address space, it need not be contiguous in the general case. Now we're going to just make a simplification, assume that the address space is contiguous. Typically, when the operating system is offering virtual memory, then it does offer contiguous address space. But as I just said, compilers may be used in situations where it's not being used with virtual memory, in which case the address space may not be contiguous. In which case the compiler needs to know what is the memory that's available and what is not. In any case, we are assuming that it is a contiguous address space. Even for a contiguous address space, for example, the compiler needs to know what are the addresses, what are the exact address values that are available. For example, is it 0 to 100, 0 to 10,000 or 0 to 10 million, whatever, or is it maybe the first few addresses are not available, maybe the last few addresses are not available, somewhere in the middle the address is available. Whatever it is, the compiler needs to know. And this is basically a contract between the operating system and the program developer. And when I say program developer, it includes if the program has been written in assembly, then it means the human program developer. If the program has been written in a higher level language, then the program developer includes the developer, or may not include the developer, but definitely includes the compiler, because now the compiler and the operating system are basically following the same contract, and that's why your program is going to be able to work. Alright, and then in this one of the features of this contract between the compiler and the operating system is, after you have, firstly, where is the code? So that's part of the contract. And the other part of the contract is, what is the entry point? What's the first instruction that the operating system should transfer control to? And so this is programmed by the compiler, but used by the operating system. So the compiler is going to set up this information, put it in the ELF executable, let's say, and the operating system will know where to read it from, and then it's going to set the program counter to that particular entry point, so that the control now is transferred to the program, and now the program can execute as it is expected to execute. Alright, so in this figure I'm showing as though the code is all contiguous. Typically it is contiguous, but the compiler may or may not want to keep it contiguous. But for simplicity, we're just going to assume that the code is contiguous. Also, in this figure, I'm showing that code is somewhere in the middle of the address space. Some compilers would want to keep it at one end of the address space, but keeping it in the middle is also okay. Keeping it at another end is also okay. But the important thing is that code is only some part of the address space, and there's a lot of other part of the address space that has not been used. And I'm calling it the other space right now. And slowly we are going to develop more understanding of how this other space can be organized, so that we can store other things like malloc memory and variables and things like that. Okay, and so at runtime, the space is managed. Other space is typically used to store data, and it's managed by generated code and libraries.